All right, everybody, welcome back. So now that we have reviewed the four big theorems from chapter 16, I want to just talk a little bit kind of informally at the end here about some maybe more highfalutin mathematical gadgets that will allow us to unify those four big theorems. And so this part of the talk is not going to be really something that you're expected to know about for the final exam, but I think it will make kind of a nice sort of dessert or something to kind of top off all that we've learned here in chapter 16. And so we're going to talk today a little bit about these things called differential forms. And what they really are and what they really do is maybe not something that I want to discuss today, but for our purposes today, we can think of them as these type of formal sums that you get by sort of taking a function and multiplying by some kind of formal gadget that we'll see in a second and adding those things together. So these come with like sort of different degrees to them too. So on three-dimensional space, there's 4 degrees of differential form that could occur. A 0 form, a 1 form, a 2 form, and a 3 form. And so a differential 0 form is really just the same thing as a scalar valued function f of x, y, z. Okay? Then a differential 1 form is a sum, a formal sum of the form p of x, y, z times this formal gadget dx plus q of xyz times this formal gadget dy plus r of xyz times this formal gadget dz, where again p, q, and r are just scalar valued functions. Okay, so I think we've seen something kind of similar to this when we were doing line integrals of vector fields and line integrals of functions with respect to x, y, and z, right? We saw something kind of looking like this in there. There's these kind of extra rules that differential forms abide by. And so it's not exactly the same thing as maybe what we previously saw. Or maybe there's just something a little extra going on that we'll have to discuss in a second. But before we get there, let's meet 2 forms and 3 forms. So a differential 2 form is another one of these formal sums. This one will have this form p times the formal gadget dy dz plus q times the formal gadget dz dx plus r times the formal gadget dx dy, where again, p, q, and r are just scalar valued functions. Okay, and then last but not least, a differential 3 form is just a one-term sum of the form f of xyz times the formal gadget dx, dy, dz, where f is just a scalar valued function. Okay, so this looks kind of like some things we've seen before too when we do like triple integrals, right? Okay, so there's some algebraic rules that differential forms abide by. And they're really just these rules that are put onto the formal gadgets, dx, dy, and dz, that come at the end of each term of your sum. So the most important ones here for us today are that if you have dx, dx, that will equal to 0. Same dy, dy, that equals to 0. And dz, dz also equals to 0. And then the next 3 rules kind of all go together. What they say is that if you interchange the order of one of these pairs, you negate the result. So dx dy is the same as minus dy dx. Dx dz is the same as minus dz dx. And dy dz is the same as minus dz dy. All right. So let's just kind of do an example, I think, for some kind of sanity check. So with these rules in place, we can multiply 2 differential forms together. And what will happen is that the degrees will kind of be like added together. So let's say we have 2 1 forms, omega, which is 4y dx plus 5 dy plus 0 dz, and tau, which is 2z dx minus x dy plus 0 dz. Well, if we want to multiply these together, we'll just multiply them like the way that we would multiply 2 expressions of this form, like in college algebra or something like that. And so in particular, since I made the last terms in each one be 0 dz, we can basically forget those and just do like the FOIL method on these two pieces here. So for the first terms, I have 4y times 2z times dx times dx. Okay. And then for the outer terms, I have 4y times minus x times dx times dy. That gives me minus 4yx dx dy. For the inner terms, I have 5 times 2z times dy times dx. That gives me 10z dy dx. And then for the last terms, I have 5 times minus x times dy times dy. Okay. And so we can apply the first rule here and see that the first and last terms of this sum are going to vanish because dx dx and dy dy are both 0. So that leaves us with minus 4yx dx dy plus 10z dy dx. Well, now I'll simplify by invoking the second of these rules and rewriting 10z dy dx as minus 10z dx dy. And then I can combine them together to be minus 4yx minus 10z, all times the formal gadget dx dy. Now, if I really wanted to represent this as a differential 2 form, which it is now, notice the product of two 1 forms gives me a 2 form. But I need to have some terms that have dy dz and dz dx on them. Well, I'll just add those with zeros on them. Okay, so this will be the same as really this guy here. All right, so that was fun. So now that we've got kind of the basic algebraic rule of differential forms kind of down here, let's think about how to do some calculus with these objects. So the first thing we want to talk about is derivatives, okay? And the rules governing the derivatives of differential forms are not about really these formal gadgets, dx, dy, and dz, but more about the functions, the scalar valued functions involved in these definitions of differential form. And so the main thing we're going to discuss today is what's called the exterior derivative of a differential form. And it takes an n form to an n plus 1 form, okay? And of course, since we haven't used that letter enough, we will denote this guy by the letter d. Okay, so then let's define d for a 0 form, and then that'll help us define it for all the higher forms. So for a 0 form, which again is just a function, the exterior derivative, df, is exactly the same thing that we called the differential of f back in chapter 14, I think it was. And so this is the 1 form where the scalar valued functions going into the 1 form are the partial derivatives of f with respect to x, y, and z. So we get the partial derivative of f with respect to x times dx, plus the partial derivative of f with respect to y times dy, plus the partial derivative of f with respect to z times dz. And notice that these 3 scalar valued functions are exactly the same as the components of the gradient vector field, the gradient of f, right? So that's something that will probably come back to haunt us in a minute. But moving on now, let's take a look at how you define the exterior derivative of a 1 form. Well, let's say we have a 1 form I'll call tau, which is given by p dx plus q dy plus r dz. Then we define the exterior derivative using the exterior derivative we have for the functions p, q, and r. So really, d tau will be dp times dx plus dq times dy plus dr times dz. Okay. And so p, remember, is a function of x, y, and z. So this is just that 3-term sum from the previous slide. So let's take a look at that here and maybe unpack the first term of this a little bit more. So if we have p as a function of x, y, and z, then this first term becomes the differential form, the partial derivative of p with respect to x times dx, plus the partial derivative of p with respect to y times dy, plus the partial derivative of p with respect to z times dz, now all times dx. Okay? And so now we'll just go forth and just multiply through like we sort of normally would if we were just following our nose now. So we get the partial derivative of p with respect to x times dx dx, plus the partial derivative of p with respect to y times dy dx, plus the partial derivative of p with respect to z times dz dx. And notice that the first term here becomes 0 because we have dx dx. And then the second one I can rewrite with a minus sign in front of it and write that this is minus the partial derivative of p with respect to y times dx dy, plus the partial derivative of p with respect to z times dz dx. Okay, very nice. And so if I did the same thing for the second term up here and the third term up here and added them all together, what I'd get at the end is that the exterior derivative of tau is given by this 2 form here, where the first scalar valued function is this difference of partial derivatives, the second scalar valued function is this difference of partial derivatives, and the last scalar valued function is this difference of partial derivatives. Notice that I think we have seen exactly this kind of triple of scalar valued functions that are given by these differences of partial derivatives. This was exactly the same as the components of the curl of the vector field f, whose original components are the functions p, q, and r. So that's something I think that's going to come haunt us. So we'll keep that in mind. And so then lastly, let's define for a 2 form who's given by p dy dz plus q dz dx plus r dx dy. We'll denote that by omega. Then again, the exterior derivative will define exactly the same way. We'll just take the fact that p, q, and r are all 0 forms, and we'll take their exterior derivatives and just tack them on to what was left over. Okay. And so when you simplify this guy and kind of follow all the algebraic rules that you get, say unpack each one, you get that the exterior derivative of omega is the 3 form whose scalar valued function is the partial derivative of p with respect to x, plus the partial derivative of q with respect to y, plus the partial derivative of r with respect to z. And I think we've seen that before. That's exactly the same as the divergence of the vector field big F, whose original components are p, q, and r. Okay, so all of these things are kind of going together here. We've seen now we've seen that this exterior derivative of differential forms seems to be encoding some of these things that we've seen about the gradient of a function, the divergence of a vector field, and the curl of a vector field. So there might be some connection between differential forms and vector fields. And there is. So let's kind of write this little diagram here to kind of summarize. So every 0 form is just the same thing as a function. And so those are interchangeable. And we saw that taking a exterior derivative of a 0 form gives us a 1 form, which corresponds to a vector field if you just yank off these scalar valued functions. That's the same as the gradient vector field of the original function we started with. Okay, now if you take a 1 form, that's again the same thing as a vector field if you just take the scalar valued functions and make them the components of your vector field. And we saw that taking the exterior derivative of such a 1 form gives you a 2 form that is another vector field, right? Another just collection of 3 scalar valued functions. And that corresponds exactly to taking the curl of the original vector field that you had. Okay, and then we saw that if you took the exterior derivative of a 2 form, you got a 3 form. And really the essential data of a 3 form is just a scalar valued function times that guy dx, dy, dz. So if you just forget about that like formal gadget at the end, you just have a function, and this exterior derivative of a 2 form corresponds to exactly the function that you get from taking the divergence of the vector field that you started with. Okay, so instead of remembering all of these kind of different fancy gadgets, we could remember them all as this kind of more uniform way as just differential forms and this derivative operator between them. All right, so just to summarize there, d of a 0 form is the same as the gradient of a function. D of a 1 form is the same as the curl of a vector field. and d of a 2 form is the same as the divergence of a vector field. And now, since we don't have any forms with degree higher than 3, then d of a 3 form is just sort of formally defined to be 0, and that's fine. But we won't really need that in this conversation. Okay, so then let's talk a little bit more about calculus now. So how will you take an integral of a differential form? Well, really, the one rule here is that the degree of the form needs to match the dimension of the shape you are integrating it over. So we're not going to really get into all the details of this, so let me just give you kind of moral to walk away with. So think of integrating a 0 form, which is a function. You'd integrate it over a 0-dimensional set, so like a finite collection of points maybe in space. And you can think of that as just taking a sum of those function values at those various points. Okay? And that might be a signed sum for some reason, and maybe we'll see that in a second. Okay. If you have a 1 form, p dx plus q dy plus, that should be r dz over a curve, then you can think of integrating this 1 form is the same as taking the line integral of the corresponding vector field that you get, okay? And I think we even had written our line integrals in some sense as having this as their integrand, or big R is there. Sorry about that. Okay. And so kind of in a similar vein, you integrate a 2 form over a surface in space, and that's kind of the same thing as taking a surface integral of the corresponding vector field over that surface. And you can integrate a 3 form over a solid region of space, and that's kind of just like taking an ordinary triple integral over that solid region of space of the function that corresponds to that 3 form. Okay? So with all of this nonsense in place, I want to tell you about what's called the generalized Stokes theorem. So let's let n be 0, 1, or 2. And let's let big M be a quote-unquote nice n plus 1-dimensional region of 3-dimensional space. Okay, so I'm not going to really tell you exactly what I mean by nice, but know that if you're thinking about any of the kind of regions that we've studied this semester, they all meet all the sort of sufficient criteria to be nice. So that's good. Okay, and so if n is 0, 1, or 2, then n plus 1 is 1, 2, or 3. Okay, so we're going to look at 1-dimensional regions, 2-dimensional regions, and 3-dimensional regions in space. And maybe for sort of suggestive purposes, this is the reason this is used, I don't really know. But this is kind of common, or it's kind of in the dominant discourse, that you will let this partial derivative thing attached to M denote the boundary of M. Okay, and so what exactly do we mean by that? Well, let's take a look at some picture. So here I've drawn 3-dimensional space, and I've drawn an example of each one of these kind of M's for n being 0, 1, or 2. Okay, so this first guy over here is when n equals 0, then n plus 1 is 1, and this guy M is a curve in space, and its boundary is this pair of points here. Okay? Okay. Then if n equals to 1, then n plus 1 equals to 2. So this region M is a surface in space. And so I've just drawn some kind of funny looking surface here. And its boundary is a collection of closed curves. Okay, so the one that I've drawn here has just this one boundary curve at the top. We've seen an example, I think, before, that kind of pair of pants that had 3 boundary curves. And we've certainly seen examples of closed surfaces that have no boundary curves. So the boundary would be the empty set. Okay, and then this last example here is when n equals 2, then n plus 1 is 3. And this nice 3-dimensional solid region of space we'll call M. Its boundary is a surface, like the sphere that is the surface of this solid region here. Okay, and so then if sigma is a differential n form on 3-dimensional space, the generalized Stokes theorem says that you can take the exterior derivative of sigma, that will now be an n plus 1 form, and you can integrate it over the n plus 1-dimensional region, M, and that is the same as taking the original sigma and integrating it over the n-dimensional region that's the boundary of M. So these two integrals are the same. Okay, so then let's try to apply that given what we know about these exterior derivatives of these differential forms. Well, then when n equals 0, this guy yields exactly the same thing as the fundamental theorem of line integrals, namely that the line integral of the gradient of a function is the same as just taking the function and evaluating it at the endpoints of the curve and taking the difference. Okay, when n equals 1, this gives us the Stokes theorem that we learned from section 16.8, for which Green's theorem was a special case. So really this tells us the three-dimensional version of Stokes theorem. So what did that one say? That if you had a surface integral of the curl of a vector field, that you could replace that for a line integral of the original vector field along the boundary curve. Okay, another fun consequence in this realm is that when our surface, M, has no boundary curves, then let's go back here again, then we can say that if we're going to take the integral of, say, the curl of some vector field, the surface integral, then we can reduce that to an integral along the empty boundary of the original vector field. But that integrating over the empty set should give you 0. So if our surface is closed, then the generalized Stokes theorem says that the surface integral, that should be an m there, sorry. Then the generalized Stokes theorem says that the surface integral over what should be m of the curl of f needs to be the value of 0. And I know that we saw back in, I think, section 16.7, a rather long-winded example of computing a surface integral of a curl of a vector field over a surface that was closed. And ultimately, we had these two pieces. And when we got the two surface integrals, they canceled each other out, and we got 0. And it was all this work just to get the number 0. And the reason that that worked out was because the vector field that we started with was the curl of another vector field. And so when you have that, you have this nice result that you can apply and do literally no work to compute that surface integral. Okay. And then when n equals to 2, this generalized Stokes theorem gives us exactly the divergence theorem, namely that if you were going to do a triple integral of the divergence of a vector field, then that is the same as just doing the surface integral over the boundary surface of whatever region you have in question of the original vector field. Okay. And so one last thing to note about all of this is its similarity to the sort of fundamental theorem of calculus. Right? We have integral of a derivative of an object equals just that original object evaluated at the endpoints. You use this one all the time. And so in some sense, this is really just the Stokes theorem in not three-dimensional space, but just one-dimensional space, just the real line, r to the 1. Right? So there's really more general Stokes theorem for really n-dimensional space. For today, we really just wanted to talk about the three-dimensional one. The picture there is beautiful enough, I think, to end the course with. And what better way to end it really than to go back and look at, the most important thing you've probably ever used in calculus, which is the fundamental theorem of calculus. What we have here is really just a generalization of that to some kind of higher dimensions. All right, well, that was great. And so I've had a lot of fun here. So we'll see you.